Okay. There's a beam of light on my face because I'm illuminated by God. Okay. So, anyways, uh, this is the USACO gold contest that happened last week, and I started this contest in silver. I was hard stuck in silver for I think like almost 3 years now, and it's like the first time I actually got past silver. Silver was pretty easy. I think like the solutions everyone can probably understand it. And then I also got past gold. I think this gold contest was actually like surprisingly easy. Uh, like anyone who has I'd say like probably like 1 or 2 years of experience in CV could get past it pretty easily, or even less maybe. It didn't require any. It didn't really require any algorithms. It's just barely some thinking. Okay, let's start. So this is problem one, minimum longest trip. Okay. So, oh no, that's problem two, boys. Okay, so this is the problem one, flight routes. So you're basically given the input is so the input is the parity of the number of flight routes between two cities. The number of flight routes. A flight route is just a path, right? So a path from suppose it's from 1 to 5, it can go to 1 to 2 to 3 to 4 to 5. That's a flight route, or it's just 1 to straight up to 5, and it gives you the parity of the flight routes for each for between every two nodes. Okay. So as you see the input, okay, I think in contest. This is my contest notes where I drew out everything. So this is this was my representation for the first this initial input here. So we can see like in the input, 1 connects to 2 to 3 to 4 to 5 with all parity of 1. So it's basically like this, and I drew it out here. So for here, so it seems pretty complicated if we start from the beginning, right? Since from the beginning it can connect to other nodes, which can connect to other stuff, which makes the answer very complex. So what if we start at the end? So if we start at the end, we can start at this node 4, right? So 4, there's one flight route to 5, but then there could only be one path from 4 to 5. So you must connect 4 to 5, right? And then you start at node 4. So at node 4, no, this is node 3. So at node 3, there's no connection to node 4. So absolutely you cannot connect it at all. And from node 3 to 5, there's one connection, but initially there's no connection here, so you have to connect it, right? And then we're on to node 2. Node 2, there's a connection to 3, and there's no other way, so you have to connect it. But once you connect it to 3, it's already connected to 3 is already connected to 5, so you don't have to additionally connect it to 5. There's a 0 there. And then for 1, it's basically the same as the other nodes. So there seems to be a strategy here. So the general strategy here is to go from reverse, and from reverse you can connect to the next node forward. If the next node forward, based on the parity, you can connect it or you don't connect it. So, for example, 4 and 5, there's a parity of 1, you connect it. 3 and 4, there's no parity, so you don't connect it. Once you connected it, if you look at the example of 2, once you connect 2 to 3, then you have to add on all of the parity, or you have to overlay the answers of 3. You have to overlay the answers of 3 onto 2. So you have to take all of the flight routes from 3 and the parity of those, and then lay them onto 2. And how do you do that? You do that through XOR, right? So basically, that's the general idea for this equation. And let me find it. So the intended solution is O(n) cubed, but you can solve it with O(n) squared with bit set. So first you connect the nodes, and then you start from reverse, and then you go to the next node forward. And if if the goal is different from what you have right now, then you have to connect it manually, or you have to add a new direct flight. Once you add a new direct flight, it changes the flight routes of the current one. So the current one has to XOR the flight routes of the one you connected it to, and then you can just keep taking the answer, and then keep going. So at every place, we only add a direct flight. We only add it if it's different. So only if we need to add it. We only add it if we only need to add it. Okay. So this question was pretty easy. You could solve it O(n) cubed. So I didn't even need to use bit set, but I still did. Okay, problem 2. So problem 2, you have n towns. So you have n nodes and m edges. And basically it gives you a directed acrylic graph, which means a directed graph with no cycles. And you're trying to find for each node, find the longest trip with the lexicographically minimum sequence. Okay. So this question looks pretty complex, right? So you have to find the longest path for every node with the minimum lexicographic sequence. So let's first look at the partials, right? So for the first partials, all labels are the same. If all labels are the same, then all paths are basically treated equally. So you just find the longest path for each node. How do you find the longest path for each node in a directed or in a graph with no cycles? So you reverse the graph and you can run a topological sort. If you reverse the graph and run a topological sort, then you can go from the sinks, and then every time you move one, you add, or I guess you add the distance is +1, +1, +1, and then you go all the way to the start, and then reverse graph, run a topological sort, then you can find the longest distance. It's kind of like DP. I'm pretty sure you've done that before. Okay, 7 to 8 are inputs. Okay, if all labels are distinct. So if all labels are distinct and you're trying to find the minimum lexicographic sequence, then a sequence that is lexicographically smaller is the same length is if at the first position which they differ, the first sequence is a smaller element than the second sequence. So the first position which they differ, if all elements are unique, then all the paths will differ at their first element, and only the first element matters. So for this partial, you only need to keep track of the latest edge, or the latest edge label, or the latest edge value, and you compare the edge values. If they have the same distance, if they reach here with the same distance, you only have to compare the latest one, right? Okay, so that's basically like 50%. For NNM smaller than equal to 5,000, you can basically keep track of the entire path. I didn't code this partial, but you can basically keep track of the entire path and just compare the paths. And then the faux solution. Okay. So for the faux solution, the problem with the all distinct labels is that after a place where, okay, imagine this is the last distinct, these are two paths of the same length, right? And this is when they're last distinct. All of these along this line, all of these are the same. So once you're here, once you're at this end node, then all of these then how would you able to tell which one do you take? So my thought process here would be, I'm just going to make the one that is lexicographically smaller arrive first. It's going to arrive first and update the answer here first, and it won't allow a bigger one to update the answer. So how would you achieve that? So first, you can run the topological sort as a BFS. So as a BFS, if it's a BFS, then paths of the same length will arrive at the same node at the same time. So at the same layer, kind of. So it arrives at the same layer. But how do you make sure, like, in that layer, like, this is the layer that these two paths like arrive here. How do you make sure in that layer the smaller lexicographic one arrives first? So you can create, so the topological, so first it's based off distance, then it's based off its value. So if its value is smaller, it gets placed further in front in the BFS. Its value is smaller, it gets placed further in front in the BFS. Okay, so imagine this was 3 and this was 5. So 3 would get placed in front of 5. But now you're here. And these have the same value. So imagine this was 1, this was 1. So how do you make sure 3 is still placed in front? Well, you can make sure 3 is still placed in front by saying, oh, since 3 came first last time, we're going to keep putting him in first. So we're going to keep putting him in front of 5. So first, it's based off this BFS first is based off distance. Then it's based off its ID. And if its ID is the same, then it's based off the time. So historically, who came first? And you keep going. If it's all the same, then 3 will arrive in first. If there's another node that's different, imagine this is 5. And now this is 3. Oh my god. This is 3. So since it's based off distance and then ID and then time, then this will override the time, and then it'll take, and now I'll put this guy first. I'll put 3 first and then 5. So basically that's my idea for this question. Just make sure the lexicographically smaller one arrives first, and then it'll update the answer first, and it won't allow the other one to update the answer. So let's see, taking the input, this is a reverse graph, and then make a priority queue, and then push in all of the sinks. Okay, so let's look at the priority queue. So the priority queue first is based off distance. So it's a BFS, and then if the distance is the same, it's based off its label. So the one with the smaller label is put in front, and then if the label is the same, then it's based off time. And what is time? Time is just I set time as like a running variable that is here the entire time. Like it's just a running variable. And then the time that, if it was historically placed in front of the other guy, then it'll still be placed in front because it's lexicographic or whatever. So then if it's historically placed in front, then it'll keep getting placed in front. So that means if it's the same distance, then the paths with the smaller lexicographic whatever will arrive first. Okay. So that's basically problem 2. It's probably the hardest problem in this set, but it's all pretty easy still. Okay, so problem 3. So Farmer John has n barns at X points, right? And then he wants to have all the shipments delivered to some point. So there's n points on this line, and you're trying to get all the points to a singular point. But then if you go right 1 unit for every barn, or every point, if the point wants to go right, it goes it takes a cost. If it goes left, it takes b cost. For Q queries, find the fewest amount of hay bales if he chooses the goal point properly with given AB. Okay. So this is a pretty standard problem, I would say. So imagine if A and B are the same. If A and B are the same, then that's a very standard problem, right? So that would be like the warehouse problem, where if all the points need to get to a single point. If all of like the shipments need to get to a single warehouse, where do you place the warehouse? You place the warehouse in the middle or in the median of all the points. So if you place it in the median, then all of the points on the left would have to, or if it's on the median, then there's an equal number of shipments on the left and on the right. And if you move it off the median, if you move the warehouse off the median one, then the answer, okay, then there'll be more warehouses on one side than the other side, and that means they will have to move more. Okay. Shit, how do you prove this? So suppose there's like 5 points. It's best to place the warehouse in the median, like here, because that means the other two, the points on the left and right, the points they have to travel is the same. But if you instead place the warehouse here, then the 3 of these guys have to travel over. Okay, that proof is sus. Go search up the warehouse problem. But for the warehouse problem, there's going to be a center minimum. The minimum is going to be at the median. But now with A and B, with different values of moving left and right, that means the answer will not be at the median. But then, still, the answer should be a concave function. Not concave. It should be a unimodal function where there's a minimum. It should be a function where it's like it should be a function like that. Since if you move it more left, if you move it more right at a certain point, the answer will become less and less good. Something like that. Okay. Just think about it. Why it's a unimodal one? It's a question left up to you. So because of this, then you can just simply do binary search over it and find the lowest point. It's pretty simple. So the binary search is basically you manage holy shit, I have like 4 versions of this thing. So first you can do since it's up to 10 to the 6, you can do a prefix sum or a suffix and a suffix of the number of steps it takes for all the people on the left to come to this point, or all the people from the right to come to this point. So this is basically the prefix and the suffix. And then you do a binary search on which location to place the point on, or place the warehouse on. And this, okay, I heard you can do ternary search, but I'm not really sure if it might be better. I have no idea, but like a binary search of mid and mid plus 1 works. So if you do mid and mid plus 1, then if the mid is smaller than mid plus 1, then you go more to the left. If not, you go more to the right. And this is just standard binary search. And this OK function is just calculating the answer. It's just the prefix plus times y. It's a suffix times x. And basically it's like that. And then you output the solution. So the reason why I have all these versions is because there could be there could be non-distinct points for the barns. And I was first doing binary search over the positions of, I was just placing the warehouse on the position of the barns. But since they're not distinct, that means like on a unimodal function, there could be a place where it's like it's flat. And if it's flat, this binary search just breaks. Yeah, so that's why you have to do it on the x, or just get rid of the distinct, or get rid of the non-distinct values. Okay, so yeah, that's basically this USACO gold contest. I would say this is probably significantly easier than what it normally is, since like a lot of people promoted. Jesus. Yeah, a lot of people promoted, and yeah, it honestly wasn't that difficult. Devin did not promote. Okay. Yeah. Dude, this could have been a silver contest, but whatever. I tried to do the platinum contest, but yeah, let's not talk about that. Yeah, so that's basically it. Silver contest was pretty easy. One of my friends got stuck on the bronze contest. Yeah, so that's basically this year's USACO, and see you guys.